Hi everyone and welcome to today's session. So in the previous few videos, if you have followed my videos, then you will know that we were studying about the classical linear regression model, where so far we have covered these things. Firstly, we found out what will be the OLS estimators of the parameters, namely alpha and beta. So we found out what is alpha cap OLS and what will be beta cap OLS. Now, in the previous two videos, I have covered why beta cap will be the blue estimator of beta, and we have also seen why alpha cap will be the blue estimator of the population parameter alpha. So this much we have covered. Now, in today's video, what we will do, we will find out what will be the unbiased estimator of the error variance. Now, if you have seen my assumptions video, there I have told you that the error variance should be homoscedastic. Homoscedastic means that the error variance has to be a constant, namely sigma square. So we said that error variance is sigma square. So in this video, we will be, deriving what will be the unbiased estimator of this sigma square. That is, we will find out what will be sigma cap square, and such that the expected value of this sigma cap square will be exactly equals to sigma square. This is what is means by unbiased, right? This we have covered multiple times. So let's see what will be the value of sigma cap square that will give you an unbiased estimator of sigma square and how we will derive it. So let's start. So firstly, we will start with the model itself. The model is like this. Yi is alpha plus beta xi plus epsilon n. So this is our simple model. Then what will be y bar? Y bar is simply alpha plus beta x bar plus epsilon bar. What will be then yi minus y bar? Yi minus y bar is this alpha will cancel out. Let me write it once. This minus this. So what will happen? This alpha term will cancel out and you will have now, this is what? This is the deviation form of yi. So this will be simply small yi. If you haven't watched my previous videos, I will give the link of the playlist in the description so you can check that out. There I have described this. When you take deviation from the mean, arithmetic mean, you will have the deviation form which is written as small y. So small yi. And here you will have beta xi plus epsilon I, and here you have minus beta x bar minus epsilon bar. So what you can do, you can take beta common. So you will have xi minus x bar plus you will have epsilon I minus epsilon bar. Now again, this is the deviation. This is small xi basically. So what we can write, small yi will be nothing but beta small xi plus epsilon I minus epsilon. So this is how you convert the entire model into the deviation form. Now when you have that, what you can write as the residual. This is the residual. This is not error. This is the residual, means the estimated portion of error. This will be simply yi minus y cap. So now what you can do, you can subtract a y bar and add a y bar. So you can write it in this way, yi minus y bar, and then take minus y cap minus y bar. So I have done this. I have subtracted y bar here and I have added y bar here. So here you have minus, here you have minus, so it will be plus. So that y bar will cancel out. This is just another way of writing this. Now, what we know, y cap, the estimated or the predicted model, this will be alpha cap plus beta cap xi. So what will be y cap bar? Y cap bar is simply alpha cap beta cap x bar. Again, we have y bar equals to alpha cap plus beta cap x bar. So what do you understand from these two things? See these two things carefully. Then what will be the relationship between y cap bar and y bar? Yes, you got it right. It simply means y bar and y cap bar are exactly equal. Right? Y bar and y cap bar are exactly equal. Right? Okay. Now start with the residual. Epsilon I cap. So this is yi minus y cap. This we have got like this yi minus y bar minus y cap minus y bar. Now this yi minus y bar is simply small yi minus, instead of y cap, now what you can write? See, y cap is this, alpha cap plus beta cap xi. Alpha cap plus beta cap xi. And instead of y bar, what you can write? Y bar is this. So alpha minus alpha cap minus beta cap x bar. Now what are the things that will cancel out? This alpha cap and alpha cap will cancel out. So you have yi minus, take beta cap common, so you will have xi minus x bar, or small yi minus beta cap small xi. So this will be the form of epsilon I cap, which is the residual, right? Okay. Now, this can be further written as yi. Replace this yi now. What is yi? We derived previously. This is yi. This is yi. So we will replace that. What will you get? Beta xi plus epsilon I minus epsilon bar. Right? This is what we have. Yeah. Then you have minus beta cap xi is as it is. In the next step, what you can do? Epsilon I cap is simply, this will remain, and from the remaining part, if you take xi common, see, from the remaining part, so from this and from this, if you take xi common, what will you have? You will have beta minus beta cap. So this will be beta minus beta cap, right? This is the form. So now what you will do? Epsilon I minus epsilon bar, now make it minus. So it will be beta cap minus beta xi. So this is the final form of the residual. This is the final form of the residual. Now what we will do? We will find out the error sum of square. So firstly find out what will be this square. Square will be a minus b whole square formula. Here we will apply. This is the first term a and this is minus b. This entire term is minus b. So a minus b whole square formula, if we apply, we will have epsilon I minus epsilon bar whole square plus beta cap minus beta whole square xi square minus 2 into epsilon I minus epsilon bar into beta cap minus beta into xi. Now what we will do? Sum of square. Error sum of square means summation I from 1 to n ei cap square, which is also called the residual sum of square, which we have used in case of derivation of the OLS estimator. So we have minimized this particular expression. This is nothing but, this expression is nothing but residual sum of square, which we have minimized while using the OLS. So what we will have, individually take sum on each of these terms. Plus you will have beta cap minus beta whole square summation I from 1 to n xi square minus 2 into summation I from 1 to n epsilon I minus this beta cap minus beta into xi. Now what we will do, expected value of this error term, expected value of this residual. Take expectation on this individual term. So this is one term, this is the second term, and this is the third term. So take expectation on each of them individually. So you will have expectation of summation I from 1 to n, epsilon I minus epsilon bar whole square, right? Plus expectation of this beta cap minus beta square will come out. See, here you have beta cap minus beta square, expectation will be, and then expectation of I from 1 to n xi square. This is the second term. And then you have a third term, which is expectation. Then what do you have? Summation I from 1 to n, epsilon I minus epsilon bar, beta cap minus beta into. Okay. So we have this much. Now what you have to do? See, you have three particular terms. This is the first term, this is the second term, and this is the third term. Now you have to manipulate each of these terms. 1, 2, 3. Let me call this the first term. Let me call this the second term. And let me call this the third term. So now you have to individually manipulate each of the term and find out the simplified version of them. So let us first work with the first term. What is the first term? And then we will, combine them to find out what will be this value. So that is what the process is. Summation I from 1 to n, epsilon I minus epsilon bar whole square. So how do you simplify it? Simply break the square. Expectation. Summation I from 1 to n. First, do the inside part. What will this be? Epsilon I square plus epsilon bar square minus 2 epsilon I epsilon bar. So now expectation of, take the summation. I am doing it step by step just to make you understand the entire thing. If you can do it directly also. So this will be this plus you have summation epsilon bar square. Epsilon bar is summing up n times. So it will be n epsilon bar square. And then minus 2 into epsilon bar comes out and you will have summation I from 1 to n epsilon I. Okay. Now what will this be? If you see, now if you take the expectation, first term will be summation, then expectation. Summation, expectation of epsilon I square. See, so I have taken the expectation on this first term, then take it on the second term. So what will this be? Plus n. And then what you can do? You can break this I from 1 to n epsilon I whole square. See, this is n epsilon bar square. What is epsilon bar? 1 by n summation epsilon I and whole square of that. So do that, minus 2 into expectation of. See, what do you have? 2 epsilon bar and then you have summation this. So again, you can break this down. So this will be summation I from 1 to n. Here you will have 1 by n into epsilon I into summation as it is. See, I have, written this second part as it is, but this epsilon bar term, I have written it in this way, 1 by n summation epsilon. Now simply put the values. What will be the values, respective values? So what is this? This will be simply sigma square. And then previously you have a sum, so it will be n sigma square. Sum is from 1 to n. So n times if you are adding sigma square, it will be n sigma square plus here you have a n. And then inside you have 1 by n square. That will come out to be n square. And then expectation of summation epsilon I square. So expectation of, Now expectation of summation xi square, how do you break it down? While doing the variance, I have told you how to do this. This will be simply like this. I naught equals to j epsilon I epsilon j, right? Now minus 2 into this 1 by n, take out this 1 by n here. Now you have expectation, and then what you have, summation I from 1 to n. Here it will be again the same thing, same as this particular thing, summation epsilon I whole square. So it will be again epsilon I square plus double summation I naught equals to j epsilon I epsilon j. Right? Okay. N sigma square plus this is 1 by n. So if you put the expectation inside, it will be 1 expectation of epsilon I square. And now plus double summation I naught equals to j expectation of epsilon I epsilon j. And then you have minus 2 upon n summation I expectation of u, not u, epsilon I square. And then plus double summation expectation of epsilon I epsilon. So this is all you have. Now, what can you say about this particular term? Can you say something about this term? Yes, this will be 0. Why 0? Due to non-autocorrelation assumption. Non-autocorrelation assumption. All right. So what will this be? This term is nothing but sigma square. This term is nothing but sigma square. So let us see. If you simplify, this first term remains the same. And then here you have 1 upon n. 1 upon n into this. This will be n sigma square, right? There is a summation here. So n sigma square. 1 by n into n sigma square. And then what you have? This second term will be entirely 0. And then you have minus 2 upon n into again n sigma square, right? So this is what you have. Now what you can do, you have to simplify. This n will go out, this n will go out. So n sigma square plus you have sigma square minus you have 2 sigma square. So that can be written as n sigma square minus sigma square. So this will be n minus 1. So what do you get? You get the first part that we started with is equals to n minus 1 sigma square. Now similarly, you have to work with the second part and the third part. So let us start with the second part and see. What was the second part? This one. Expectation of beta cap minus beta square into summation small xi square. So expectation of beta cap minus beta square into small xi square. Now can you tell me what will be this portion? This portion is nothing but variance of beta cap, right? This is nothing but variance of beta cap. And then you have this to be as it is, this. Now, in the previous videos, I have found out what is variance of beta cap. You can refer to that video. I am here writing the final answer that this will be sigma square by summation xi square, I from 1 to n, into you have this same thing here, this. So this and this will cancel out, and the second part, the value of the second part is simply sigma. So the first part is n minus 1 sigma square, the second part is only sigma square. Now find out what will be the third part, and then we will combine everything and find out the result. So this is the third part. Let me write the thing for you. So third part is 2 expectation of summation I from 1 to n epsilon I Then you have beta cap minus beta xi minus epsilon bar beta cap minus beta, and then you have summation xi. See, this is what you have. Yes, so basically we have combined. Yes. Have we done this right? No, we haven't. Sorry for this. So this will be 2 expectation of summation. This was the term. Epsilon I minus epsilon bar. And then you have beta cap minus beta into xi. This was the term. Okay. So 2 expectation. Now what you can do, you can individually multiply it. So take this epsilon I and multiply with the rest of the thing. So that is what we will do. Epsilon I, then you have your beta cap minus beta into xi minus epsilon bar. Now take the second term and then multiply with the rest of the thing. So epsilon bar, beta cap minus beta, and then you have summation I from 1 to n xi. All right. Now we have to find out what will be this term. Let me do it here. What will be this term? So this is basically if you apply the expectation. Here you have an expectation. So expectation will be here. So expected value of epsilon bar beta cap minus beta. I'm not taking the rest of the part because this is only involving xi. Xi is non-stochastic and expectation will not be on this xi. So only this portion. So expectation, this can be written as 1 by n summation I from 1 to n epsilon I. And then here, if you have seen my video on blue of beta cap, then you will know what can we write about this. We can write it to be wi epsilon I. I have said in that video why we can write in this way. I have derived the entire thing. You can check that out. And if you have seen the video, you might recognize this term. So beta cap minus beta can be written in this fashion in terms of epsilon I. So this is a linear combination with wi being the weights. Okay. So 1 by n, if you apply the expectation, it will be summation I from 1 to n expectation of epsilon I. And then you have summation I from 1 to n wi into expectation of epsilon. Okay. So what is this and what is this? Expectation of epsilon I is 0, expectation of epsilon I is 0 from the assumption of our model. So this entire term is 0, this entire term is 0. So the second part, this entire thing is 0. So we don't need to include that from the next line. So what we can write, this will be 2 into expectation of only this first part. Epsilon I, then you have beta cap minus beta into x. And we don't need to, the rest of the thing is 0. Okay. Now 2 into expectation. Now see, again, beta cap minus beta is wi epsilon I. Since the summation is here previously, you don't need to write that again. So this is wi epsilon I, and then you have an xi. So 2 into expectation. This will be summation I from 1 to an epsilon I square. And then you have wi and xi. 2 into expectation. What is wi? Wi is xi into summation I from 1 to n small xi square. And then see here you have another xi, so it will be square. So wi is basically xi upon small xi square. Again, refer to previous videos. Right? Now what you do? Take the expectation inside. Take the expectation inside and calculate. So 2 into what do you have? Summation I from 1 to n. Expectation of epsilon I square into xi square upon summation I from 1 to n small xi square. So this is sigma square. So 2 into sigma square into This summation will come to xi square 1 by n xi square upon summation I from 1 to n xi square. So this will cancel out. Third part becomes 2 sigma square. Right now, so we have all the three parts. Now all we need to do is to combine them and to find out the final answer. Let's get back. So we started with this expression, expectation of summation ei. This will be cap square. See, this was ei cap square. So we are just taking expectation on both sides. So it will be ei cap square. So let me write expectation of ei cap square summation. Summation I from 1 to n ei cap square. That was equals to 1 plus 2 plus 3. So first, what was the first value? It was n minus 1 into sigma square. Second value was only sigma square, and the third value is 2 sigma square. So what will be this? N minus 1 sigma square. Sorry, this was minus 1 plus 2 minus 3. Yeah, see here you have a minus 1 plus 2 minus 3. So this will be minus sigma square. So n minus 1 sigma square, or it will be n minus 2 sigma square. So what do we get? Let me summarize. What we get is this summation I from 1 to n epsilon I square is nothing but n minus 2 into sigma square. So what you can do, take this n minus 2 inside this 1 by n epsilon I cap square, then take this n minus 2 and you will get sigma square. And if you look at my first slide, I have told you we need to find out what will be this value. See, we need to find out what will be this value. So if you compare these two expressions, if you compare this expression and you need to compare this expression, because we started with the question that what will be the unbiased estimator of sigma square. So this portion we need to find out. And if you compare this expression, what will be the expression then? The expression of sigma cap square will be simply summation I from 1 to n, this upon n minus 2. I hope you got the process. So this is the entire derivation, and this is nothing but the unbiased estimator, where sigma cap square is the unbiased estimator of sigma square, right? And what is the numerator then? What is the numerator? You can write it in another way. Sigma cap square is nothing but RSS by n minus 2. So what is the unbiased estimator for sigma cap square? Sigma cap square is nothing but the error variance. Basically, sigma square is the error variance, and this is the estimator. This is the unbiased estimator of the error variance, which is in two variable simple regression model. This is simply RSS by n minus 2, and this is the entire derivation. Now, I want to mention one result here, and after that, I'll end this video. So here what we see is, look at the denominator. Here you have 2, n minus 2. So for two variable model, with two parameters, sigma cap square will be RSS upon n minus 2. But in general, not but, in general, for a model with k parameters, sigma cap square will be RSS upon n minus k. So this is the thumb rule. So in a model with two parameters, in any CLRM model, when you have only two parameters, which is the case for classical linear regression model, two variable regression model, then here you will have 2. But in a model which is a multiple regression model, suppose instead of 2 parameters, I take 3 parameters. I consider 3 explanatory variables, 3 parameters. In such a model, you have k equals to 3. So here you will have RSS by n minus 3. And in general, for a model with k parameters, if in a model you have k number of parameters, then your sigma cap square will be RSS by n minus k. Right? So in general, you don't have to derive this thing again and again. You know the general result. This can be considered as a thumb rule. You can apply it for your convenience, right? This is a thumb rule for any model. If you know the number of parameters, you know what will be sigma cap square. And later on, when we will do hypothesis testing, this will come very handy to you. So please remember this result. So let me quickly recap what we have done in this video, and then I will stop. So we wanted to find out what will be the unbiased estimator of sigma cap square, which is nothing but the estimator of error variance. Error variance is sigma square and sigma cap square is the estimator of error variance. So we started with our original model and we converted everything into this particular deviation form. After that, we found out what is the residual. What will be the general form of the residual. So for that, we have calculated all these things. This was the general term, general residual term. This was the final form of the residual. Once we have residual, we can find out the square of residual and then take summation. So firstly, we have taken square of this. Then second step is to find out the summation of squares, sum of squares. So what will be that is the residual sum of square basically. Residual sum of square, and then we have manipulated this residual sum of square. Expected value of the residual sum of square we have manipulated, which give us these three things, three parts, and then we have individually solved these three parts, and then we have simply combined this to get this estimator. So this is how you find out the unbiased estimator of sigma square, simply expected value. See, the expected value of this estimate is equals to the actual population parameter. That is the reason why it is unbiased. Okay, that is the property of unbiasedness. So you call A cap is a unbiased estimator of A when expected value of A cap is just equals to A. And this is the property that is being satisfied here, that in the inside part, this inside part, this is the estimator basically. If you take the expected value of the estimator, that is exactly equals to the population parameter. And that will give you this result as well, that if you have two parameters, you will have this to be the unbiased estimator. And if you increase the number of parameters, you go to a more complex model with more explanatory variables and more parameters, then in general, this is the thumb rule that this will be your unbiased estimator. I hope you find this video helpful. If you do, please, subscribe to this channel and give me a like for this video. And that gives me immense motivation to continue making such useful videos to you. And in the next session, I'll be going into the decomposition of total sum of square into explain sum of square and residual sum of square, and we will see how to derive the entire. So stay tuned for that. And thank you for your